welcome to ORgano. Now before starting to this video, I want to say that some interesting thing, and that I will try to solve some important questions, okay, for your competitive exams. Now, so for this I am taking some questions of different types of books, which is very much useful and very much important for your exam purpose. Okay, now you can get those questions on the description of this video, and you can try yourselves, and I will try to solve this in details of those questions in next video. Okay, so let's start. Now this is our oxidation reaction part 4. I hope this is my last video of oxidation reaction series. Now I think I will cover all those topics related to this oxidation reaction, and in this video we will discuss also some different type of oxidation reactions. Okay, so let's start. Now at first I am taking a important oxidation reaction, that is Oppenauer oxidation reaction. Okay, so what is the basic important is interesting thing is the oxidation reaction, that you have taken a alcohol that is 2 degree, and you have to put the acetone, and this is the main reagent, that is aluminium isopropoxide. Okay, now this 2 degree alcohol you can get a ketone over here, and this is your side product. Now what is the mechanism and what is the importance of this Oppenauer oxidation reaction? Now there is a major important thing is that if a compound contain 2 degree or 1 degree, both of them, then this oxidation can selectively oxidize this 2 degree one. Okay, so 2 degree will much more react than 1 degree. And there is one more important thing is that there is no chance of over oxidation, that is alcohol to ketone, not ketone. It always convert that alcohol to ketone, but not ketone to carboxylic acid. Okay, so this is the overall thing, and this is so much chemoselective reagent, and it's a reversible reactions also. Now you can see here, this is a mechanism I am written here, that is a reversible sign. Okay, this is all a reversible process. Now let's have a look the mechanism. Now this is your 2 degree alcohol, and this you will put this aluminium isopropoxide, the reagent, and you have put this acetone. So acetone is basically activate of this aluminium isopropoxide. Okay, so how it will activate? It will activate this oxygen has a lone pair of electron. The lone pair of electron attack over this aluminium center, and this oxygen attacked over this center. Now there is a leaving of 1 mole of isopropanol, that is this hydrogen, and 1 mole of this IPRO, that is isopropanol, will leave from the system. Okay, so this is your overall product after this removal of isopropanol. Now there is an important thing is that there is a shifting of hydride from this alcohol hydride transferred to this acetone, and there is a formation of 6-membered cyclic transition state, that is this one. This is your 6-membered cyclic transition state. Okay, this is very much important. Now this hydride transferred over here. Okay, in this way. So this is the overall process, and this is your intermediate. And now there is a formation of this bond, and there is a formation of this ketone, and this bond will attack, and this aluminium will contain this oxygen as a covalent bond, not a direct covalent bond. Okay, so this is, and you will get this final product, and this is from your side product. Okay, so this side product is formed due to this acetone. Okay, so this acetone will reduce to its alcohol, and this alcohol is oxidized to its ketone. Okay, so this is the overall Oppenauer oxidation, and the important thing is that there is 2 degree alcohol is much more reactive than 1 degree, and it is a reversible in nature. Okay, and one more important thing is that there is no chance of over oxidation. Okay, so this is the important and is very much chemoselective reagent as well. Now this is your overall Oppenauer oxidation. Now there is a reverse process also, that is Meerwin-Pondorf-Verley reduction. That is in general it is called MPV reduction. This MPV reduction is just opposite of this Oppenauer oxidation. Okay, I will discuss on this overall MPV reduction on my reduction series. Okay, so this is all over this Oppenauer oxidation. Now there is one more important oxidizing agent, that is manganese based reagent. There is some manganese based reagent also oxidize some alcohol to ketone. Okay, now I am taking two examples here over here. Now see, this is manganese MnO2 and presence of acid. Acid is nothing but just solvent, and you have two different type of alcohol. That is, one is benzylic alcohol and another is part is called allylic alcohol. Okay, so the MnO2, that is manganese dioxide, is very much selective, and it generally oxidize the benzylic alcohol rather than this allylic alcohol. Okay, so benzylic alcohol will react faster than allylic alcohol. So what will be your product? Your product is look like this. This is your aldehyde. So this is your overall product. This part will selectively oxide. That's because of this is a benzylic position and this is allylic position. Okay, the question also comes from this topic and in CSIR-NET GATE and IIT-JAM also. Okay, here is another important example is that you have given this MnO2 and after that you have given this type of ylide. Okay, so first when we use the manganese dioxide, the MnO2, what will be your product? So we all know that what will be the product, that is, this is our product, that this is your CHU. Okay, so this is your product. Now you have given this ylide. Okay, so we all know that the selectivity of ylides, that is that this stabilized ylide, always gives E-alkene, and the unstabilized ylide always gives Z-alkene. This is the selectivity, the chemoselectivity of this ylide chemistry, and you can get those things in Clary and Caruthers or in any best books. Okay, so this is and how now there is a question, that is how can you identify it? How will you identify it as which one is stabilized or other which one is unstabilized? Okay, so for this you can check this, if there is a electron withdrawing group in present of this ylide, that is if I am written this ylide like this way, the bond I am breaking this bond this way, that is CO2Me. Okay, so this negatively charged about the carbon center will goes to resonance of this with this CO2Me group, so it will much more stabilized. Okay, if some electron donating group is present over this negative over this position, so it will be unstabilized. Okay, so this is your stabilized ylide, and I will say that what I am saying, that stabilized ylide always gives this E-alkene selectively. Okay, so this ylide is stabilized, so it generally gives this E-alkene. Okay, so this is your product. I am not doing the overall mechanism. I will discuss some of these topics on this this is actually Wittig reaction. I will discuss of these topics on Wittig reactions. Okay, so this is the overall process. Now you have to know one more important thing is that this is Fissner-Moffatt oxidation. This is another important oxidation reactions. So now let's have a look and what is the mechanism of this Fissner-Moffatt oxidation. Now this is your 2-degree alcohol, and you have given this TCC and this TMSO and TFA. This is just kind of acid. Okay, so this TCC may vary. Okay, so the generally if we're doing this mechanism, so we generalize this as like this way. That is, this is R and this is R, and this part is just fixed. And this R, in case of TCC, the R group is this one, that is cyclohexyl. So this is your R part, that is your R3 is like this in case of DCC. Okay, so now let's have a look the mechanism and how the reaction proceed. Now this in presence of acid, this nitrogen has a lone pair of electron. This will take a proton first from here, and after that, now this step is actually the activation of DMSO. Now we all know the structure of DMSO. We already knew that Swan oxidation, Corking oxidation. If you haven't checked yet, you can go over here. I will attach the link of those videos. So that is part 1 and part 2. You can get easily, and what will be the structure and what will be the products. Okay, so this, now see, this has a negative charge over this oxygen atom, and this will attack over this carbon, and this will bonds go here. Now there is a formation of the products. Okay, I am written over here, that is, there is no space actually. NH and R3 is oxygen. Okay, so this is your product. Now there is a second step, which is activation of alcohol. That is activation of alcohol. Okay, so activation of alcohol, that is you have to take this type of intermediate, and you have to put this alcohol. Okay, so I am written over here. And we have taken this alcohol. So this oxygen has a lone pair of electron, so it will attack over this sulfur atom, and then you get the product like this. It is R N double bond C NH R3, that is R3. This has the oxygen. You get the sulfur over here. See part R1, R2, and there is a sulfur methyl, and there is CH2, and I am written this hydrogen like this way. Now there is a important, that is not a rearrangement, or the somewhat a rearrangement like this way. This takes up a proton over here, this will go here, and this will go here. Okay, now after that there is a formation of the removal of this dialkyl urea. I am written the structure over here, and that is NH double bond O NH R3. This is your dialkyl urea. And what with this we will get this part. Okay, this part also, that is CH3 is CH2 minus positive charge over sulfur, and the hydrogen here, the R and R1 R2. Okay, now there is a formation of product like this way. Okay, so you can get your final product like this, that is R1 R2. Okay, so this is the overall importance of this Fissner-Moffatt oxidation. The Moffatt oxidation is generally called Moffatt oxidation, and you have to put this type of reagent, and you will get a final answer. Okay, so this is the important thing. Now let's come to the another important thing, that is tempo. Now what is tempo? So you have to know the structure of tempo. So tempo is nothing but this. Okay, so this is your tempo. So tempo is generally called 2 2, that is if I numbering from here 1 2 3 4 5 and 6, so that this is 2 2 and 6 6. So 2 2 6 6 tetramethyl piperidine, 1 oxyl. So oxyl group is this one, and this type of ring is called piperidine. Okay, so this is piperidine. So this is a derivative of piperidine. Okay, so it has also a selectivity, that this type of tempo, so this type of reagent generally oxidize 1 degree carbon or 1 degree alcohol rather than 2 degree alcohol. Okay, so it generally selectivity shows that 1 degree alcohol is faster oxidized than 2 degree. Okay, so now how to form this tempo. Now for this you have to put, I am written here, on 2 dimethyl 2,2,6,6 dimethyl piperidine, you have to put this one. You have to, that is W, that means tungsten in presence of EDTA. Okay, it can form this one to this one. So this is your tempo. Okay, so now tempo has a important role, that is very much selectivity. I already said that this is 1 degree alcohol. Via the mechanism goes via single electron transfer method, that is ACT method, single electron transfer method. Okay, so now see, so if we take a compound like this, so this compound contains 2 types of alcohol, that is this one is 2 degree, this one is also 2 degree, and this one is 1 degree. So I said that tempo generally oxidize 1 degree carbon over 2 degree 1 degree alcohol than 2 degree. So it shows this one as a major product. Okay, so this is the overall conditions of tempo. Now one more important oxidizing reagent, that is Des-Martin reagent. Okay, so what is Des-Martin reagent? So Des and Martin, they are 2 scientists. They form this type of hypervalent iodine system, which will oxidize alcohol to ketone. Okay, so this is your 1,2-iodobenzoic acid. This iodobenzoic acid in presence of potassium bromate and in presence of an acid, this form IBX. Okay, so this is your IBX, 2-iodobenzoic acid. Okay, so this is your iodoxybenzoic acid. This is your IBX, and you have to put this Ac2, that is acetyl anhydride, in presence of acid. We will get this type of reagent, that is iodine 3 OAC over here, and this iodine has the oxidation state of 5. This is your hypervalent iodine. Okay, this is called Des-Martin reagent. So this is called this Des-Martin reagent. Now let's have a look that how the Des-Martin oxidation reaction, how Des-Martin reagent oxidize the alcohol to ketone. Okay, now see a mechanism of this Des-Martin reagent. Now we are taking this one OAC, 3 OAC over here of this iodine, and you have to put this. If we take RR, this is secondary alcohol. This oxidizes one pair of electron and it will attack the iodine center, and this OAC will leave from the system. Now after that there is a formation of this thing. Okay, like this, and here you have the OAC, and this you get R1, R2, and here is the hydrogen. So you have free the acid OAC minus is free from the system, so this has a free, this will free from the system and leaves the anion, and this negative charge over takes the proton from here, the bonds goes here, and this will go here, and this OAC leaves from the system. So you will get that if your desired ketone with this side product. Okay, that is only OSC. So this is your overall dismarting region. So this is not for all those students which are prepared for JAM or like others examination. This is not also important for CSIR also. So you can check it out from different books, and this is very much important for your general knowledge actually. Now there is a last and important thing is that ruthenium tetroxide, RuO4. So this RuO4 has an important role, and this shows different selectivity in different type of with co-oxidant actually. Okay, so what type of co-oxidant that is? If we use RuCl3 in presence of NaI4, it generates in situ ruthenium tetroxide and oxidize this triple bond actually, double bond. So you can get the overall part will remain same. So overall part will remain same, and this part also remains same, and from here you will get the acid. Okay, so it will convert directly acid using in presence of RuCl3 and NaIO4. Okay, so this is an important criteria. If we use this RuCl3 in presence of oxone, that is a neutral solvent. Okay, so if we use this oxone, that is oxone means KHSO5. Okay, this is also used as co-oxidant. Used as co-oxidant. Okay, so this type of reagent with this RuCl3 it generally forms this overall part remains same, and this part will oxidize as CHO. So this is your selective reagent also. This overall part remains same, but this alkene group, it will convert this alkene to this aldehyde or this acid in presence of different type of co-oxidant, that is NaIO4 if we use oxone like that. Okay, so this is a different case. There is another important case, and there is a formation of lactone. There is an important method to form lactone from this cyclic ether to a lactone. That is this one. The other parts same. I am not written over here. This is the other part. So the all was same. If we use RuCl3 in presence of NaI4 and with this cyclic ether, this cyclic ether generally forms this type of lactone. Okay. This is the overall concept and overall mechanism of those things, and we have done different type of oxidation, and this is very much huge for your preparation, and this is also important for your any kind of preparation. Okay, so I hope this video is useful for you, and this is the last and final topics. I covered all these topics related to these things. Okay, so thank you so much for watching. Have a great day.